Okay, so let's apply the angular momentum concept to some of the examples. The first one is going to be, let's take a solid sphere of some mass m. Let us say it is moving with some angular velocity omega. Okay, it's a solid sphere. Let the radius of the sphere be r, and we want to find the angular momentum of this object. Okay, and we'll use our definition: L equals I times omega. That's it. Now you know what I is for a solid sphere. It's 2/5 mr square. We'll multiply this by omega, and this is essentially what we are looking for. So this is simply, if you know I, finding moment of inertia, finding the angular momentum is very simple. Okay, and if you know the angular momentum, we could also find the kinetic energy of this object, and kinetic energy is, if you recall, it is equal to 1/2 times I times omega square, okay, which also happens to be equal to 1/2 times, if you look at I is L over omega, so L over omega square, L over omega, no, what am I doing? Oops. We know omega is L over I, so I can leave I the way it is, and then rewrite this as L over I square, and you can rewrite this as L square over 2 times I. Okay, this is very similar to Ke equals P square over 2m. Okay, so there are a lot of similarities that go between translational motion and rotational motion. And once you know L rather, you can just plug it into this equation and find the kinetic energy for this object. So it will be 2/5 mr square omega, the whole square, divided by 2I, and you can all evaluate this very quickly as 2 over 25 times the I. So you know what? I'm complicating life. So it'll be 1/5 m. There's no omega here. 1/5 m times r square. So 2/5 m r square times omega square. That's what we end up getting. Okay. So we have all our expressions here. Everything is cool. All right, great. In the next, let's look at another problem here, and this is an example of a seesaw situation. Okay, so you have a seesaw. You have a man of mass m. You have a girl of mass lowercase m, and let's say they're both sitting on the ends of the seesaw. Okay, and we would like to figure out what the angular momentum is for the entire system about the seesaw. Okay, and let's say that at some point the angular velocity is some omega about this point. Okay, now to find the angular momentum, we'll use our expression I times omega. Okay, and let us find the moment of inertia for this entire system. Let us say that the plank itself is a plank of mass m, and its length is obviously 2r. So so the I is, when we do I, we have to be very careful. We have to account for I for everything. Okay, we can treat the two people at the ends as particles, and so their moments of inertia will be m times r square plus capital M times r square. And now we have to get the moment of inertia for the rod also, and what we know is that the moment of inertia for a rod about its center of mass is 1/2 m times L square. 1/12 m times L square, so it will be 1/12 m times 2r the whole square. Okay, so if you do this correctly, what you'll end up getting is mr square plus mr square 4 over, so this is the 1/3 mr square. We can just call this m prime rather to separate it from the mass of the dad. And so we get m plus capital M plus m 1/3 of m prime times r square. So this gives us the total moment of inertia, and now we can figure out the total angular momentum. It is equal to m plus capital M plus 1/3 of m prime times r square times omega. Okay, so we know the angular momentum, and once you know the angular momentum, what we can also do is we can figure out the angular acceleration of the system, just like the previous problem. Okay, what would be the angular acceleration? So we can do this by using our expression dl by dt equals tau equal to I times alpha. Okay, so what we'll do is let's figure out the net torque. We already know dl by dt. Okay, it is simply going to be equal to all this m plus 1/3 m prime times r squared times d omega by dt, which will give us an alpha. And so now all we need to do is figure out the net torque, and the net torque is going to be the sum of the torques due to the dad and the girl. Okay, now at some angle, let's say that this angle is some angle theta and theta. Okay, the force of the dad is going to be m times r, the girl's force is going to be lowercase m times r, and if this is the angle theta here, okay, then we need to make sure that we take the correct angle. The angle that the dad makes with the moment arm is going to be equal to pi over 2 plus theta. No, this will be pi over 2 minus theta. Okay, and same thing for the girl. Okay, she'll make an angle of pi over 2 minus theta as well. So what we know is that the net torque is going to be equal to m times r, m times g, the weight, okay, times r times sine of pi by 2 minus theta, and then the girl's torque is going to oppose the dad's torque, and that's going to be equal to lowercase m times g times r times sine of pi by 2 minus theta. Okay, it could be plus theta, but it will end up being the same thing, because what you get is mgr cosine of theta minus lowercase mgr times cosine of theta, which is equal to m minus m times g times r times cosine of theta. Okay, now as we said, all this is equal to the dl by dt, and when you do dl by dt, what we get is m plus capital M plus a third of m prime times r squared, and then when you do d omega by dt, I end up getting alpha. So this gives me alpha. Alpha is m minus m times g, okay, times cosine of theta divided by m plus capital M plus third of m prime times r. So you can find the alpha, and then there are other things we can do with this problem. Okay, so check out this is another example from the textbook. Check this out, make sure that you understand what you need to do.